You are looking at a number on a screen, 73.5, and a physicist who already has a Nobel Prize sitting on his shelf is telling colleagues that number might mean the textbook description of the universe is wrong. Not slightly off, not in need of a footnote. Wrong in a way that would require physics nobody has written down yet. That number is a measurement of how fast the universe is expanding. And for a decade, it has refused to match the number a completely different method keeps producing. This is the channel where we take the space stories that flash by in a headline and give them the full explanation they actually deserve. If that's your kind of rabbit hole, subscribe and settle in, because this one involves two Nobel-level astronomers, the same space telescope, and two answers to the same question that still will not agree. The telescope at the center of this is the James Webb Space Telescope, which launched on December 25th, 2021 from a spaceport in French Guiana, and now orbits the Sun about 1 million miles from Earth, at a gravitationally stable point called the second Lagrange point. Its primary mirror is 6.5 meters across, built from 18 hexagonal gold-coated segments, more than 6 times the light collecting area of the Hubble Space Telescope. It was designed to eventually succeed. Webb sees primarily in infrared light, which matters enormously for one specific reason. Light from the most distant galaxies has been stretched by the expansion of the universe itself on its way to us, shifting it out of visible wavelengths and into the infrared. The farther away something is, the more that light gets stretched, a phenomenon called redshift. Webb was purpose-built to catch that stretched light, which means it was purpose-built to look further back in cosmic time than any instrument before it, closer to the very beginning of everything. Webb itself was decades in the making. Formal development began in the late 1990s under the working name the Next Generation Space Telescope, and the project spent years absorbing delays and cost increases before its eventual launch, becoming a joint effort between NASA, the European Space Agency, and the Canadian Space Agency, with the final total cost across its full development history estimated at roughly $10 billion. The telescope was eventually renamed after James Webb, a former NASA administrator, who oversaw much of the agency's early crewed spaceflight program in the 1960s, a naming choice that has itself drawn scrutiny and debate within parts of the astronomy community over Webb's tenure at the State Department during a period of anti-gay government policy, though NASA's own internal review found insufficient evidence directly tying him to those policies to justify renaming the mission. Unlike Hubble, which orbits close enough to Earth that astronauts could physically service it, Webb sits roughly 1 million miles out, far beyond any current crewed spacecraft's reach, which meant every one of its systems, including a 5-layer sunshield the size of a tennis court that had to unfold perfectly in space, needed to work correctly the first time, with no possibility of a repair mission. To understand why astronomers cared so much about pushing that far out in distance and that far back in time, it helps to understand what redshift actually measures. As light travels across billions of light years through an expanding universe, the space it is moving through is itself stretching, and that stretching lengthens the light's wavelength along the way, shifting it toward the red end of the spectrum and eventually out of visible light entirely into the infrared. The more a galaxy's light has redshifted, the longer it has been traveling, and the further back in cosmic history astronomers are actually looking. Researchers estimate redshift 2 ways: a faster, rougher method called photometric redshift, based on how bright an object appears through different color filters, and a slower, far more reliable method called spectroscopic redshift, which uses an instrument called a spectrograph to split an object's light into its full range of individual wavelengths. Webb's NIRSpec instrument was specifically designed to perform that second, more rigorous kind of measurement on galaxies fainter and farther away than any spectrograph had reliably managed before. That capability is what caused the first shock. In February 2023, an astronomer named Ivo Labbé, working at Swinburne University of Technology in Australia, published a paper in the journal Nature describing 6 candidate galaxies that Webb had photographed as they existed between 500 and 700 million years after the Big Bang, when the 13.8 billion-year-old universe was roughly 3 to 5% of its current age. According to standard models of galaxy formation, galaxies at that age should be small, disorganized clumps of young stars still in the early stages of pulling themselves together out of gas and dust. What Labbé's team found instead looked mature. One candidate appeared to contain roughly as many stars as the present-day Milky Way, packed into a volume around 30 times more compact. That initial estimate came from photometric redshift, the faster but less certain of the two distance techniques, which meant the entire finding rested on an assumption that could, in principle, turn out to be wrong. Follow-up teams using Webb's NIRSpec instrument to obtain full spectroscopic measurements of other similarly early, similarly bright objects did confirm that at least some genuine galaxies exist at these extreme redshifts, including one cataloged object designated GNZ11, spectroscopically confirmed to be a galaxy observed roughly 430 million years after the Big Bang, with unusually extreme properties for its age. That confirmation mattered, because it ruled out the simplest dismissive explanation, that the whole population was a redshift measurement artifact, and none of these objects were really as early as they appeared. The remaining, harder question was never whether early massive galaxies existed at all, but how many of them there were, and how massive the real ones actually turned out to be once every source of contaminating light was properly accounted for. Joel Leja, an astronomer at Penn State and a co-author on the paper, put it plainly in a public statement at the time, saying the discovery upended what many researchers had considered settled science. The team started calling the objects universe breakers, informally, because if the mass estimates held up, something in the standard timeline of galaxy formation would have to give. Labbé himself admitted the team's first reaction was disbelief, describing the moment in a later interview as leaving them mind blown and, in his words, kind of incredulous, since nothing in existing models predicted galaxies that massive appearing that early. Science moved quickly to test the claim, and that testing produced the second discovery 1 year later. Brightness, which is what Webb actually measures, is not the same thing as mass. Mass has to be inferred, and that inference depends heavily on assumptions about exactly what kind of light source is producing the glow, whether it comes primarily from stars or from something else entirely. In 2024, a researcher named Katherine Chwarovsky led a follow-up analysis and found that a meaningful share of the apparent brightness in these early compact reddish objects was coming not from stars, but from actively feeding black holes. Astronomers had started calling this broader population of compact red sources little red dots, and once the black hole contamination in several of them was accounted for, the inferred stellar masses came down substantially from Labbé's original estimates. This was not a retraction. It was science functioning exactly as it is supposed to. An extraordinary claim triggered rapid follow-up, and the follow-up genuinely revised the picture. The little red dots themselves turned out to be far more common than the original 6 universe breaker candidates ever suggested. Across Webb's various deep surveys, astronomers have now cataloged several hundred of these compact reddish objects at similarly early cosmic times, and the working picture that has emerged treats many of them as a mixed population, some hosting actively feeding black holes whose glow can mimic the light of an enormous number of stars, others still plausibly hosting the kind of unusually massive mature stellar populations that first got everyone's attention. Untangling which is which for any individual object generally requires the same kind of detailed spectroscopic follow-up that NIR-SPEC was built for, and that follow-up has not been completed for the entire population. Researchers have also noted that the black holes powering at least some little red dots appear to be unusually overmassive relative to the galaxies hosting them, heavier, proportionally, than the relationship astronomers had already established between galaxies and their central black holes in the nearby present-day universe. That is its own open puzzle, sitting alongside the original mass question, since it suggests either that supermassive black holes can form and grow unusually fast in the early universe, faster than current models of black hole growth generally allow, or that something about how astronomers estimate black hole mass at these extreme distances is itself producing an overestimate. Both possibilities are currently being investigated, and neither has been ruled out. But revised is not the same as resolved. Even with the black hole correction applied, a residual population of galaxies from this early era remains harder to explain under standard assumptions than researchers expected before Webb ever launched. And as recently as this year, a 2026 analysis using a large cosmological simulation called UCHAI-UU has argued that some of Labbé's original stellar mass estimates still cannot be reconciled with standard theory, keeping the underlying question open even after the loudest version of the claim was walked back. While that debate was unfolding around individual headline-grabbing galaxies, a separate and in some ways more fundamental disagreement was deepening elsewhere in Webb's data, one that does not depend on any single object being unusual. It concerns a number called the Hubble constant, which measures the current expansion rate of the universe, expressed in kilometers per second for every megaparsec of distance, a megaparsec being about 3.3 million light-years. The disagreement did not begin with Webb. Edwin Hubble first measured the universe's expansion in 1929, and for decades afterward, the uncertainty on that measurement was so large, with estimates ranging anywhere from about 50 to 100 kilometers per second per megaparsec, that the two modern methods' results comfortably overlapped and nobody considered the question urgent. That changed gradually through the 2000s and 2010s as instruments improved and both sides of the measurement tightened. Riess's S80ES team published increasingly precise local measurements throughout that period, and by 2019 the gap between their result and the Planck satellite's cosmic microwave background value had become difficult to dismiss as coincidence, prompting the first widespread use of the phrase Hubble Tension in the scientific literature. What Webb changed was not the existence of the disagreement, which had already been building for roughly a decade, but the ability to test specific proposed explanations for it with a level of precision no earlier instrument could offer. Measuring it at all requires what astronomers call the cosmic distance ladder, a chain of overlapping measurement techniques where each rung is calibrated against the one below it. The bottom rung relies on parallax, the tiny apparent shift in a nearby star's position as Earth orbits the Sun, which gives astronomers a directly measured geometry-based distance with no assumptions required. That geometric baseline is then used to calibrate the true brightness of Cepheid variable stars in the same and nearby galaxies, since a Cepheid's brightness and its pulsation period are tightly linked in a relationship discovered in the early 20th century. Once Cepheids are calibrated, they, in turn, are used to calibrate the true brightness of type Ia supernovae, since a handful of galaxies happen to contain both Cepheids and a supernova, allowing the very bright, very distant supernovae to serve as reliable distance markers reaching billions of light years further out than individual Cepheids can be resolved at all. Every rung in that ladder carries its own small uncertainty, from the exact geometry of a parallax measurement to the precise relationship between its Cepheids period and its brightness to whatever dust and stellar crowding effects might be quietly biasing a distant supernova's measured brightness. And those uncertainties compound as the chain gets longer, which is precisely why a 4 times sharper telescope like Webb, capable of resolving individual stars more cleanly at every step, was expected to help settle rather than deepen the debate. There are 2 independent ways to calculate this number. The first works backward from the cosmic microwave background, the faint afterglow of the Big Bang mapped in extraordinary detail by the European Space Agency's Planck satellite, combined with the standard model of cosmology to predict what today's expansion rate should be. That method consistently produces a value close to 67, 4 kilometers per second per megaparsec. The second method works forward from the present day, using nearby pulsating stars, called Cepheid variables, as reliable distance markers, then calibrating exploding stars, called type Ia supernovae, against those Cepheids to measure distances much farther out, and finally converting all of that into a present-day expansion rate. That local method, led for years by Adam Riess and a team called SHOES, consistently produces a noticeably higher number, in the range of 73 to 74 kilometers per second per megaparsec. Riess shared the 2011 Nobel Prize in Physics with Saul Perlmutter and Brian Schmidt for the discovery, using supernova data, that the universe's expansion is not just continuing but accelerating, a finding that first established the existence of what astronomers now call dark energy, that gap between 67, 4, and roughly 73. 5 does not sound large on paper, but by the standards of precision cosmology, it is enormous, and it has been getting harder to explain away rather than easier. Researchers describe the discrepancy as exceeding 5 standard deviations in several independent analyses, a statistical threshold well past the point where scientists would normally attribute a mismatch to random chance or simple measurement noise. For years, the leading hope was that one side of the calculation contained an unaccounted for systematic error, something subtle in the instruments or the calibration that was quietly skewing one method relative to the other. Webb gave researchers a genuine chance to test the hope directly, because its sharper resolution, roughly 4 times better than Hubble's, can separate individual stars in distant galaxies that Hubble's images blur together into a single smudge, a known problem called stellar crowding that some scientists suspected was artificially inflating Riess's local measurement. In February 2024, Riess's team published the results of that specific test in the astrophysical journal Letters, using new Webb observations of 5 galaxies that had together hosted 8 type Ia supernovae, containing about 1,000 Cepheid variable stars in total, reaching out as far as a galaxy called NGC 5468, located about 130 million light-years away, and the most distant galaxy where Cepheids had ever been individually measured. If crowding had been secretly inflating the local expansion rate, Webb's sharper eye should have revealed it and pulled the number down toward agreement with the Planck measurement. It did not. The Webb data confirmed the original Hubble measurements were reliable across the full distance range tested. Riess described the outcome as leaving behind what he called the real and exciting possibility that our understanding of the universe is incomplete, since the most likely mundane explanation, a hidden measurement error, had just been ruled out by the sharpest telescope available. Not every team working this problem agrees that the mystery is deepening. In May 2025, a separate group called the Chicago Carnegie Hubble Program, led by Wendy Friedman at the University of Chicago, published its own analysis in the Astrophysical Journal, using Webb and Hubble data together, but relying on a different set of distance markers than Riess's team, the tip of the red giant branch, a class of aging, low-mass stars that reach a sudden, predictable flash of brightness late in their lives, along with a related population known as carbon stars. Applying those methods across 11 galaxies, Friedman's team calculated a Hubble constant of 70, 4 kilometers per second per megaparsec, with a margin of error around 3%, a value close enough to the Planck measurement of 67. 4, that the two results' uncertainty ranges technically overlap. Friedman argued publicly that this overlap suggests there may never have been a real conflict to begin with, framing years of tension as largely a byproduct of accumulated systematic errors in the older Cepheid-based method rather than evidence of new physics. Other researchers were not convinced. Dan Skolnick, an astrophysicist at Duke University, publicly noted that Friedman's own central value still sits closer to the high end of the disputed range than to the low end, calling it surprising that her team would present the result as ruling out the tension altogether rather than simply narrowing it. That disagreement has not settled down as 2026 has gone on. Reporting on Riess's team's most recent measurements, released this spring, put their updated combined Webb and Hubble result at 73, 50 kilometers per second per megaparsec, with an uncertainty of about 0.81, essentially unchanged from years of earlier local measurements and still standing well apart from both the Planck value and Friedman's overlapping result. Riess has continued to argue publicly that the most straightforward remaining explanation for that persistent gap is that scientists have not fully written down the physics governing how the universe has expanded between the early cosmic microwave background era and today, potentially involving dark energy that changes in strength over cosmic time rather than staying constant, an idea that gained additional support from a separate 2024 analysis of galaxy positions by the Dark Energy Spectroscopic Instrument, a ground-based survey operating out of Arizona that has mapped the three-dimensional positions of tens of millions of galaxies and quasars since it began full operations in 2021. That survey's results, released in 2024 and expanded further in 2025, found hints, not yet conclusive, that dark energy's strength may be evolving rather than fixed, a result that unsettled cosmologists, specifically because it points in the same general direction as Riess's expansion rate discrepancy without either result fully confirming the other. Beyond evolving dark energy, researchers have floated a handful of other explanations for the Hubble tension over the years, each still speculative and each carrying its own problems. One idea, sometimes called early dark energy, proposes a brief burst of additional repulsive energy in the universe's first few 100,000 years, though matching its effects to the cosmic microwave background data without breaking other successful predictions has proven difficult. Another proposes that our galaxy happens to sit inside an unusually large, unusually empty region of the universe called a local void, which could locally distort expansion measurements, though most cosmologists consider a void large enough to explain the entire discrepancy to be in tension with other independent observations. None of these alternatives has gathered anything close to consensus support, and researchers surveying the field have noted that more than 1,000 separate papers have now been written attempting to resolve the tension through one mechanism or another, without any single proposal managing to explain the full discrepancy while also remaining consistent with every other established observation of the cosmos. None of this changes anything about daily life on Earth, and it is worth being precise about what is and is not at stake. A revised Hubble constant does not alter gravity, does not change how satellites orbit, and will not affect a single GPS calculation people rely on every day. What it would change, if the tension turns out to reflect genuinely new physics rather than a subtle measurement error, is cosmology's account of the universe's age, its ultimate size, and its long-term fate. Trillions of years from now. The kind of number that appears in textbooks, planetarium shows, and every calculation of how the cosmos evolved from the Big Bang to the present moment. To put a concrete number on that stake, a Hubble constant of 67, 4 versus 73. 5 translates into a difference of roughly 1 billion years in some estimates of the universe's age, depending on exactly which cosmological model is used to run the calculation backward from today's expansion rate to the Big Bang. That is not a rounding error inside a scientific paper. It is the kind of figure that appears in museum exhibits, introductory textbooks, and every planetarium show that opens with a line about how old the universe is, and it would need to be revised if one side of this debate turns out to be right for reasons the other side has not yet identified. It is also, less abstractly, a live demonstration of how science actually functions at its edges. 2 respected, well-funded teams, using the same telescope, applying different but individually defensible methods, and currently arriving at different answers to one of the most basic questions you can ask about the universe. That is not a failure of the scientific process. It is the process working in public in real time before consensus has caught up with the data. And it is a useful reminder that even a settled sounding number like the age of the universe rests on an active, ongoing measurement rather than a fixed, permanently closed calculation, one that professional cosmologists are still actively revising in published journals as this video is being made. As of today, the debate remains unresolved on 2 separate fronts that both trace back to the same telescope. On the galaxy formation side, the most extreme individual claims from 2023 have been meaningfully walked back, after accounting for black hole contamination in 2024. Yet a residual population of unusually massive early galaxies still resists full explanation under standard models, as recent analysis published this year continues to argue. On the expansion rate side, Riess's team's newest results from earlier this year show no meaningful narrowing of the gap with the cosmic microwave background measurement, even as Friedman's competing team continues to argue the opposite conclusion from data drawn from the same two telescopes. Friedman's group has already announced plans to target a cluster of galaxies called COMA later this year, hoping a completely different vantage point using surface brightness fluctuations in old elliptical galaxies rather than individually resolved stars, bypassing supernovae and Cepheids altogether, might finally break the deadlock between the two camps. A separate researcher, John Jensen, has already used a related surface brightness fluctuation technique to independently estimate the Hubble constant, and his results have so far landed in roughly the same disputed middle ground as everyone else's, neither cleanly resolving the tension nor cleanly confirming it, underscoring just how difficult this particular number has been to pin down using any single method in isolation. Whether that measurement arrives in time to settle anything or simply adds a third number to a debate that already has two that will not agree is not yet known. Other observatories are being built or already flying with this exact question in mind. The European Space Agency's Euclid mission, launched in 2023, is mapping the shape and distribution of galaxies across a large share of the observable sky, specifically to track dark energy's behavior over cosmic history and the Vera C. Rubin Observatory in Chile, which began science operations in 2025, is expected to independently catalog an enormous number of type AUA supernovae over the coming decade, adding yet another large, independent dataset to a debate that currently rests on a comparatively small number of individually measured objects. None of these projects is expected to produce a final answer within the next year, but each is designed to narrow the uncertainty on one side of the ladder or the other, gradually, the same slow way most genuine resolutions in cosmology tend to arrive. What remains genuinely open is not a small technical footnote buried in a supplementary table. Researchers still do not have an agreed explanation for why two independently defensible methods of measuring how fast the universe expands keep landing on different answers, using data from the same space telescope built specifically to eliminate that kind of ambiguity. They still do not have full consensus on how a residual population of unusually massive, apparently mature galaxies formed within the first few 100 million years after the Big Bang, fast enough to challenge assumptions about how quickly matter can assemble into stars, and whether the underlying cause turns out to be a stubborn, still undetected measurement error, or a genuine revision to how dark energy behaves over cosmic time, is a question no single observation has yet definitively answered on either side of the disagreement. A telescope built to look back nearly to the beginning of everything has ended up doing something almost the opposite of what it was funded for. Instead of simply confirming the picture cosmologists already had, it has handed two separate teams of serious, credentialed scientists two different numbers describing the same universe, and neither side has been able to make the other's number go away. Somewhere in that gap between 67, 4, and 73. 5 is either a mistake nobody has found yet, or a piece of physics nobody has written down yet. And right now, even a Nobel Prize is not enough to tell you which. What makes this particular disagreement worth paying attention to, more than most scientific controversies that get compressed into a headline, is that it will not stay open indefinitely. The instruments capable of resolving it, Euclid, Rubin, and Webb's own continuing observations, are already collecting data, and the COMA cluster measurement planned for later this year is the kind of independent third check that has historically been how these standoffs finally break, one way or the other. When it does resolve, the answer will either be almost disappointingly mundane, a hidden calibration error finally tracked down and corrected, quietly bringing two numbers back into agreement, or it will be the first confirmed evidence that the universe's expansion has not behaved the way physicists assumed for the past century, a genuinely new chapter added to a textbook that has not needed a chapter like that in a very long time. Both outcomes are still on the table. Both remain, for now, equally supported by credible working scientists using the same telescope and looking at the same sky. If you want more of these deep dives into the space stories that never get the full explanation, subscribe so the next one finds you. Tell me in the comments which side of this debate you find more convincing. And if you know someone who would want to see two Nobel-level scientists disagree about the size of the universe, send this one their way.